Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Now, in today's discussion, we're going to look at an extension of the concept of ideal gases. And of course, we have decided that from experimental data, the concept of ideal gas is going to be displaying some various aspects, whereby we see that from the ideal gas equation, the relationship between pressure, volume, and the temperature can be given using these specific variables, whereby R is the number of particles and R is the gas constant. So therefore, we're going to monitor these three specific variables and try to consider what are some of the experimental data that we're going to obtain. So in this case, from this particular illustration that I've given in terms of a graphical representation, this is going to be a relationship between pressure in atmospheres and what we refer to as a compressibility factor. Now, this compressibility factor is basically the ratio between PV and nRT, given in that specific order. Now, this compressibility factor are going to assist us try to monitor the behavior of various gases from the real perspective, which is of course going to be contradicting the ideal gas perspective that we had mentioned in our last case. Now, we had said that for a gas that obeys this specific equation, or the ideal gas formula is referred to as an ideal gas. And we said that naturally these gases are not going to be in existence. Therefore, they are not going to be particular gases which are basically going to obey this particular law. But the law provides for us a basis of describing a wide range of behavior for particular gases. And of course, we're going to see that for real gases or a mixture of gases, this can be providing for us a basis of trying to find their particular behavior. Now, in this case, the compressibility factor is going to present a graphical representation for real gases. And I've given a range of gases in this case for this is ammonia, hydrogen, methane, nitrogen, and this is ethane, given in this specific order. So therefore, the graph of a compressibility factor against the pressure in atmospheres is going to give us this particular relationship. And of course, the behavior of most of the gases still approach their ideal behavior. We're going to see that the pressure is going to be decreasing in that specific order. But as the pressure increases, we're going to see some deviation from ideality, and therefore this is going to be the normal or the realistic behavior of gases. So at high pressure, we're going to see that there's going to be a deviation from ideal behavior for large number of gases, as we're going to see. But at low temperatures, the more gases are going to deviate from ideal behavior, and of course this is going to be described using the graphical representation. Now, this compressibility factor gives us a range of values of between 0 and this. So an increase in compressibility factor, as we're going to see later, is going to have a specific implication. But if we have a compressibility factor of course 1, then that one implies that this basically is what we refer to as an ideal gas. So at this specific point, if we're seeing a compressibility factor of 1 as the increase in of course pressure, or rather this particular pressure in atmospheres, there's going to be a deviation from this ideal situation as I've mentioned. And this can assist us monitor the behavior of various gases using this particular aspect of a compressibility factor. Therefore, for a compressibility factor that is of course less than 1, whereby we're going to have a PV over nRT, which is less than 1. This of course implies that the pressure of the real gases is smaller than the pressure that is calculated by means of the ideal gas law, which we are going to obtain using this specific formula. And then we can have a situation whereby the compressibility factor of course is greater than 1. And therefore, for this particular case, the volume of the real gases is larger than the volume that is going to be obtained from the value of the ideal gas equation. And we can have this relationship given in terms of PV and RT for these two particular scenarios. So in this case, for the first case, I've said that for a compressibility factor of less than 1, this means that the pressure of the real gas are given as such. So the first one, for a compressibility factor smaller than 1, is going to consist of course the concept of a pressure, whereby the pressure of the real gas is smaller than the pressure that is calculated by means of an ideal gas equation. Now, for the second case, we have said that the volume of the real gas is larger than the volume that is calculated from the ideal gas equation. And this, of course, is going to be some of the relationship that we're going to achieve from this. Now, of essence for us is to understand that basically for real gases which are going to be monitored using this experimental data, it's going to be shown that real gases basically displayed an aspect of a deviation from ideality by using this specific graphical representation. If at all we're going to consider the compressibility factor and pressure in atmospheres given as such. So therefore, this deviation from ideality calls for us to develop a particular relationship, which is going to give basically the realistic relationship between gases in terms of pressure, volume, and temperature, and that is going to be very relevant for us, especially in trying to, or rather put them in practical applications in various areas. So therefore, in our next discussion, we're going to look at the van der Waals equation, which basically is going to bring in some of the particular adjustments to this particular real gas equation, ideal gas equation, which is going to give us a realistic sense of how these particular gases can be determined in terms of volume, temperature, and pressure for ideal, or rather for real gases. So that is it for now, guys. I hope that we have understood this particular graphical representation for a deviation from ideality, and therefore a deviation from this specific representation. And therefore, this one, as I've said, calls for another representation which is going to assist us describe the concept of real gases, which of course have displayed this deviation from ideality. So that is it for now, guys. By God bless you. Catch us in our next video.